Let's begin. Last time we left off, I want to do some coding. If you remember, we were talking about errors. The topic seemed a little simple, I understand, but I wanted it to be a segue to get some coding together. And for you to reassess your coding skills might be something you've done before. That's okay. Just bear with me as we get through these first few lectures, so everybody is approximately at the same level in terms of coding, so we can push into new uncharted territory for you. And last time we left off, we were talking about that there's like no true values in the world. Any value you get, even from a calculator, is an approximation to the true value. Like you can't really compute sine of 3 or exponential of 0.5, correct? Only in limited situations where you have integer arithmetic or working with fractions, you might get you'll get like exact answers and true values. But otherwise, everything is an approximation. And then, in the absence of a true value, how do you measure the error when you are dealing with approximations? And this applies also in practice, not just in experiments, not just in computing. And in the example we did for computing, the idea is to compare a better approximation to the new approximation that you're trying to build. And so you're comparing supposedly a worse approximation to a better approximation, and with that you define the error. And essentially you call the better approximation as the truth. So in an experimental setting, let's say you're designing a new sensor to measure radon, but then you already have an existing sensor that somehow was designed, verified, and tested, and costs hundreds of thousands of dollars. You call that the truth. There's an error in that sensor, but we're just going to call that the truth. And then you bring your new sensor and compare to that sensor as the gold standard, right? There's also uncertainty, and you can do a statistical analysis on that. We're not going to delve into that. But at least the definition of an error in practice, you should think about it as measuring compared to something that you call the truth or that you call a gold standard. So that led us to the concept of approximate error. We went through some kind of simple formulas here. And we did this example together in class for comparing approximations to a first derivative using consistently smaller values of this parameter h here. That's the rise over run. That's how much distance you go on the x-axis to see the change in the y-axis. And as you shrink that, we know you get from math theory, we know that you get better approximations. So we compare the value with the smaller h. We compare the value with the larger h to a value with the smaller h, calling the value of the smaller h as the truth. And we do this systematically from 0.5 here, h 0.5, we compare that to the value at 0.25, then 0.25, we compare that to 0.125, and so on. Okay? Now, you can also say, well, what if I call this the truth? So I compare 0.5 to this and 0.25 to this. That's okay. That's fine. You can still get a measure of the error. And that's oftentimes what we do in practice. In computational fluid dynamics, we create a solution with very high resolution in space and time, and we call that the truth, and we compare all our calculations to that value, and that's okay. But you get more insight when you systematically compare these values here, as your colleague said the other day, that as we cut the h in half, the error is also cut in half. So there's this one-to-one relation between how the h is shrinking and how the error is shrinking. Anyway, that's not the point here. The point is just getting through understanding the mechanics of this and the coding aspects. All right, so I left off here last time. If you want to bring up your Jupyter notebooks, we were going to do the approximation for this same function we're working with, 2e to the half x, and using this first forward Euler formula, we call it forward Euler formula, for the definition for an approximation of the derivative. And we want to do this for different values of h and compute the error. So we're going to run it for h equal 8, h equal 4, compute an error, from 4 to 2, compute the error, 2 to 1, compute the error, and so on all the way down. And we should continue to see the pattern we observed in the previous slide. As you cut h in half, I expect to see that the error is also being cut in half. Okay, there's a reason for that. We're not going to talk about it, but there's a reason for that. And from my understanding, yes, I should expect this. That's a way I could tell what I'm doing is correct. So now I want to do this in Python. We started doing this for h equal 8 and h equal 4 last time. And I'll show you how annoying and tedious that is. And then we'll work on coming up with a slightly better method to do some coding. Again, I'm using these as a way to get you to exercise your coding skills. If you know how to do this already, some of you might already know because you've been in some of my other courses. That's great. That's fine. It's a way to you refresh. But for those who haven't seen it, this will be a very valuable exercise. All right. So let's get your Jupyter notebook. Let me see this one. Okay. So I'm going to move this here. And so for those in the back, is this okay? Can you see this? Yeah? In the back? You can see it? Great. So get your Jupyter notebooks up and running. You all up and running? Great. Okay. So we were working with this last time, right? X equals 0.3, and we defined h. We calculated the derivative. I called it df8. So that's the df by dx, essentially, at h equal 8. So I called it df8. And I wrote the formula, the forward Euler, the function at x plus h minus the function at x over h. And I have x defined here, h here. And then we printed this, that the derivative with h equal 8 gave us this value. And then with h equal 4 gave us this value. And we were able to compute the first error, which is an relative approximate error using the better approximation and the worse approximation. Okay, so df4 minus df8 over df4, put the absolute value. I think I put absolute values in numerator and denominator. Doesn't matter in this case. They're the same. And we got this huge error, 319%, or you can keep it without a percentage if you want. Either way, it's fine. So let's continue. And I know you might be saying, this is dumb, Professor Saad. Why don't we do a loop? If you want to do a loop, go ahead and do a loop if you know how to do it. If not, I want those who are working on this to feel the pain of having to write this over and over and over and over again. Because in practice, what if I ask you to do this for 1,000 values of h? Do this for h equal 8, 4, and keep cutting it in half until I get to 10 to the minus 6h, right? You're not going to copy and paste this over and over again, right? So we will need a better way of working through this. So let's do a couple more, just to show the pain. Okay, so all you have to change now is h. So next we're going to go h equal 2, and then df2, and you're not changing anything else, right? Because this is the same thing. You could say, oh, let's put this in a subroutine. We're going to get to that. Okay, those are improvements that we will do later. But for now, let's just do it the tedious way. So we'll get to the second error. I'm going to stop printing the df. Oh, what did I do? I put a comment. How do you put a comment? You can put this, I call it the sharp signal. What is it? The pound key. In music, we call this symbol sharp. So I always call it the sharp. So put the pound key here, or you can press if you're using a Mac, it's Command / if you're using Windows, you figure it out. Okay. So I'm gonna comment these guys out. So just put the cursor anywhere and just put Command / or Control / if you're doing Windows. And so let's do the second error now. And we'll do the second error. So this will be E2. And this is going to be df2 minus df4 over df2 times 100. And that will be E2. And we will call that second error. OK, it didn't do anything. It gave, oh, that's right, df4. Thank you. All right, so we went from 319% to 85%. OK, now we're getting into Here we were in the noise because h was so large, 8. Probably the theory doesn't hold true anymore because the derivative tells you that h needs to be small. Okay, so when you're using h equal 8, that's a relatively large value. So it needs to be actually smaller than 1 for this to be true. So we will continue. Let's do another one. Let's do for h equal 1. So we keep cutting in half. And df1, I'm going to call it. I don't need this. And then e3, this will be df1 minus df2 over df1. And we're going to print e3. Third error. All right, now we're getting into something 85, 32. We can continue doing this, okay? But it's annoying, right? And it's silly, okay? It's bad. It's a bad idea because you're using Python as a calculator. And that's ridiculous. Python is not a calculator. Python is a programming language. You need to use it as a programming language. Otherwise, just use your calculator or Excel. Okay, so how can we improve on this? Give me some ideas. If you know how to code, give me some ideas too. If you don't, what do you think? How do you think we can improve?
Can we define two functions, one being our regular function and our derivative approximate?
Okay, so your colleague is saying, let's define, so this df2, so we will define a function for what we want to differentiate and another function for how we're computing the derivative, right? So one function is going to be 2 math e to the 0.5x, and the other one is a general function that computes derivatives. We're going to do this actually further in a few slides. Now, I'm not going to call, just to set the standards moving forward, it will be easy to get things confused between function in Python and function in math, because this is a function, right, exponential, but what is also a function in Python? What function are you talking about? And then we start fighting and arguing and misunderstanding each other. So from here onwards, the word function will be reserved to mathematical functions, sine, cosine, exponential, logarithm. I'll tell you, take your function and put it in Python, and then you're going to tell me, do I put it in a function in Python? No, don't say that. We're going to say we're going to put it in a subroutine in Python, okay? So when I say let's make a subroutine in Python to implement this mathematical function, now we're clear. You're saying I want to write the code that calculates this mathematical function. Okay? Simple convention. It doesn't have to be that way, but it's one convention to make sure we're clear. Okay, so this is good. We can create that, but I want something more. What's bothering me is so even if I did a routine to call this function and do it, I have to call it every time here. Agreed? For df2, I still have to have a line that's called df4 and df2 and df1 to call that subroutine. I didn't reduce the amount of lines. The problem here is the h values. We need, yes?
We can use the range of h values of the vector.
Okay, and then do what with that?
Apply to the df.
Okay, so apply the df function on that range. Okay, that's exactly what we want to do. So what your friend is saying, again, the problem is that we have all of these h values and we're repeating them. It would be smarter if we put all of these h values in a bin and just go over the bin, say pick every value in the bin and apply the same thing over and over again, because we are applying the same thing over and over again. We're copying and pasting. It's ridiculous. We should have one set of lines of code that just grab something and repeat the operation. That's what programming is about. Okay, so now how do we repeat this? We need to put the h values in an array, just like I had them in the slides. I put them between like these two brackets, and I had these values. So we need to put them in that array and operate on that list, on that bin or that array. Now, anything you put in a list in Python or in any code, we generally call that array. It's a common word. I think everybody understands what that means. What's even more powerful in Python is that you can operate in arrays just by applying something directly on those arrays. So let me show you how we can do this. Okay. So first, let's do this. Okay. So let's call this a better way. So I'm going to change this into a text cell and just say a better way using arrays. So what I will do, I will first declare, before we work with h values, let me introduce the idea of arrays. Anything in Python that is in brackets is some kind of array. We call them generally a list. So I can say x is equal to 1, 2, 3, 4. And that is automatically a list, an array. You can access it by saying x0 or by indexing these values. So let me actually change the number so you're not confused by indexes and values. So 3, 33.33, 7.3345, 8.2, and 4.87. Okay? Now, to access values in this list, you simply call the x variable where we put this list in and access the index. The indexing, what is an index? It's just simply the location of an entry in the list. And we always start at 0. So x at 0 is 33.33, x at 1 is 7.345, x at 2 is 8.2, and x at 3 is 4.87. In Python, we always index starting from 0. Okay, in MATLAB, if you've done MATLAB, you index starting from 1. But the cleaner indexing is to start from 0. So if I put x0 here and press enter, it's going to give me 33.33. This is how I access this value. If I put x1, it's going to give me 7.35. And then I can multiply this value, say, by 2. Okay, it's going to be, so this x1 is like a variable in its own. What it's technically doing, the computer, Python, it says, oh, x at 1, what is x? X is a list in memory. At 1, I need to figure out the second location in memory and bring this value and then multiply it by 2. So it does that for you automatically. Okay? Now, let's say I want to do another list and say that 23.1 and 33.8, 8.11, 9.5. Okay, that's another list, right? What would be cool, you might ask the following question, and it would be cool to do that. Can we define addition, multiplication, subtraction, division on lists? Can we define that? Just like we do in vectors, in real math, where you add two vectors or subtract them or you multiply them. There's different ways to multiply vectors, right? Dot product or cross product. Can we do something like this for lists? Okay, let's try it. If I go and say x times y, it's going to barf at you. I cannot multiply sequence by non-ints of type list. Unfortunately, it looks like we can't. Okay, x plus y. If I did x plus y, it did it. Okay, but it just gave me something weird. So when I did x plus y, what it did, it took the first list, 1, 2, 3, 4, and then appended the other list to it to make a new list. But that's not what I want, right? I want to add them one by one. So that's kind of one definition for addition on lists. Okay. So it turns out what we want to do is something not like this, where we're just adding two lists together. I want to be able to add each entry together. So to do this, you have to go to a different type of array or a different type of list, not the standard Python list, a type of list that comes from NumPy. So I'm going to go back here and say import NumPy. And because I don't want every time to say numpy.something, numpy.something, I'm going to give it a nickname. Okay? Because NumPy is a long word. Okay? NumPy is a long word. So I'm going to import NumPy and give it a nickname let's call it NP. So when I say import NumPy, it's bringing the NumPy library. This is numerical Python. It has a lot of cool things to do for numerical computing. It's going to be the most important library we use and you will use throughout your career. But I'm going to give it a nickname, so I'm going to import it as NP. So from now on, call it NP. Okay? So NumPy is a numerical Python library, just like the math library. Okay? Now I could have import math as M, right? You know, and then M and math are interchangeable right now. Okay? If you want. Now NP and NumPy are the same, so go ahead and put this up here and press Shift Enter. I always like to put my libraries at the top, so you know this. If you've taken any course with me or done any coding, put all your libraries that you need to import, put them at the top. All right, so what is this infamous new array that I want to talk about? It's simply a NumPy array. All right. Now, how do you create a NumPy array? Just simply by wrapping it around a list. So if I go here and say np.array, and I open parentheses, and that's it. I keep that list inside. It's a Python list. But this np.array is going to convert that list into a NumPy type array, which is a more powerful array that is very useful for computing and engineering stuff. Okay? And the same thing here, np.array, and I'm going to put it in here. Now, when I Shift Enter, nothing happens here. It's just like, OK, at least didn't give me an error. So now what happens when I do x plus y? Now it did what I wanted it to do. It added these two arrays one item at a time. So it added these guys, that's 56.43. It added these two, 41.145. It added these two, and it added these two. And what did it do? It put them, so when you add two NumPy arrays, what are you going to get? A watermelon? No, you're going to get another NumPy array, right? If you multiply two, what happens if you multiply them or subtract them? Okay, if you subtract them, it's going to subtract them. It's going to do x minus y, x is going to do x1 minus y1, x2 minus y2, x3 minus y3, or x0 minus y0, x1 minus y1, x2 minus y2, and x3 minus y3. Okay? And it's going to give a NumPy array, right? It tells you this is an array that contains these values. Okay? Now you can do y minus x is going to respect the order. Y minus x is this. What about multiplying them? X times y. Okay? It's multiplying one element at a time. Don't confuse this with the dot product. There's another way we do dot products later. We'll talk about it. But at least for now, what we've established is that with NumPy arrays, we can operate on arrays as you do on scalar values, as you do on numbers, very simply by using the same symbols for multiplication, addition, and you can also do division. Okay, so I'm going to do division here. And it does it one element at a time. First element of the first array, second element of the second array. You can add 50 arrays together. Add, multiply, subtract. It operates one element at a time. Now, this is really cool because traditionally, or with traditional coding languages like C++, Java, Fortran, these languages, to add two arrays, you have to loop over them. You have to go and say, here's a counter called I for I going from 0 to 15. Go through the first entry of the first array, first entry of the second array, add them together, store them in another array, and keep going. Couldn't get any easier. You're just simply adding two arrays together. It adds them or multiplies them, operates on them as you please. Okay? Now, this is called vectorized operations. Fancy name for saying when you do these things, similar to MATLAB, you're operating element-wise on these arrays, so you can take that for granted. They have to be NumPy arrays. If they're traditional Python lists, it will not work. You can start by creating a Python list and wrap it in a NumPy array to convert it into a NumPy array. Okay, so now this opens up a world of possibilities because now, what if I apply a function to, okay, so let's now create our h values as numpy.array, and I'm going to do 8.0. Why do I put 0.0? To make sure to tell Python this is not an integer, this is a floating point number, okay? 2.0, make it a habit, okay? Well, you're rarely working with integers, so make it a habit to put a decimal point, 0.5, 0.25, 0.125, okay? Okay, so these are my h values, okay? And NumPy array, let me put a parenthesis here, okay. So now you might ask, okay, can I apply a mathematical function on a NumPy array? Let's try it. Doesn't hurt, right? It's not like the computer is going to explode. It's just going to give us an error. So let's do math.exponential, just for the sake of it. Math.exponential h. Gave an error. Okay, why in this case? Because math, it's telling you only size 1 arrays can be converted to Python scalars. The thing is that the math library can only operate on single values, not arrays. It cannot operate on arrays. Because the math library is a simple library that just acts as a calculator for the most part. We used it previously in the first cell here, like math. We were dealing with a single number. But this is, if we were going to take this h value and put it here, these arrays, so we can vectorize the whole thing, math is not going to do the job. So what do? Well, luckily, NumPy also provides you with all of the mathematical functions that the math library provides you, except that they operate on NumPy arrays. Okay? So what I'm expecting here, exponential h, is for this to take exponential of the first value of h, and then the second value, and then the third value, and return a NumPy array with those values. Okay? So let's do this. If I do simply np.exp h, ta-da. What did it do? It took the exponential, it took the h array, and then applied the exponential mathematical function to each entry and stored it in a new array. Look at the size of this new array. It's the same size as h, right? Because this value corresponds to e to the 8. This value corresponds to e to the 4. This value corresponds to e to the 2. This value e to the 1, which is 2.7. That's the Euler's number, right? E1. And then e to the half, e to the 0.25, e to the 0.125. Okay, that's super cool. Okay? Okay. We'll talk about plotting later, because this is going to be the way we are going to plot things. Now the punchline. You see all of these things, I can calculate all the derivatives, okay, by simply applying this in a vectorized manner, right? So my x value is fixed at 0.3, and I already have, so I'm going to delete this, okay? Actually, I'm not, I can't even do undo here. Let me see, edit, undo, delete cell. Never mind. Okay, x equals 0.3, and I already have my h values. Actually, let's go up here. Okay, my h values are in this array. Now, if you want to be a good and thorough programmer, maybe give this and call it h array or h values or h vals, so that when someone is reading it, they know this is an array. So when later you're using it, they know this contains more than one value. Okay, so now I copied and pasted this line here. I claim that I can do all of these derivatives in one shot by simply replacing the math with np.exponential and np.exponential. Okay, now because NumPy is working here, I can provide NumPy with vectorized values. What it's doing here, x is a fixed value. X plus an array is simply x plus each entry in that NumPy array. Over here, this is a single value. That's OK. It's gonna work. It's magic. But then this is an array divided by another array that is a NumPy array. This should just work, right? So let's call this df values. Those are all the derivatives. And if I execute, no error. That's always good news. Now let's print df values. OK, so what does this contain, if you've been following me? What do you think it contains? If you know the answer, don't know. But what do you think this contains? Pardon me? So the derivative of each value for, so this one is the derivative using which h value? 8. This one, 4, and this one, 2, and this one, 1. And so, right? In one shot, we did all the derivatives at the different h values by being a little smart about it. Thankfully, Python provides this feature that you can vectorize the whole thing. Okay, so you can use Python as a calculator. I'm not going to give you a hard time about it. But trust me, there's going to be a point where you're not going to be able to finish the homework because I'm going to ask you to do this for 250 values of h. So you need to vectorize. This will work for any size of h vals. Whereas the other method, if I add 10 more values, I'm going to have to copy and paste 10 more times. And that's not a smart way of using Python. In one shot, in one line, I did all the derivatives because I used an array, an NumPy array for these h values. But we're not done because we need to compute the errors now. Okay? We need to compute the errors. Now, to show you how I'm going to do that, we need to switch back to the slides for a minute. Because I have the derivatives here, right? And what I need to do is find a way where I can subtract every two values from each other. So, because the first error is going to be based on the difference between these two. The second error is going to be based on the difference between these two. The third error will be based on the difference between these two, correct? Because this is df at derivative at h equal 4 minus derivative at h equal 8, derivative at h equal 2 minus derivative at h equal 4, and so on. Okay? This is really a coding exercise, not about errors, right? Okay, so let's go back to the slides so I can explain to you how I want to compute the errors. Okay. The approach that we will use is called array slicing. And that's also a very powerful way of working with NumPy arrays. Look, I can teach you to do all of this with for loops, but I know you already hate for loops. This is much easier because it does the for loop for you. It's visually cleaner. It just takes 1 extra minute for you to remember what you're doing and conceptualize what you're doing. In general, if I'm given a NumPy array, think of it as looking like this in memory. This is the memory. It contains slots. In each slot, there's a value. This is a NumPy array that contains 5.4. So A at 0 is 5.4. A at 1 is 7.2, and so on. So there's 1, 2, 3, 4, 5, 6, 7 entries in this NumPy array. Okay? You can index this array going forward. So for example, A0 is 5.4. A3 is 21.2. Agreed? Because that's the index here. At 0, I have 5.4. At 1, I have 7.2, and so on. Okay? But what's also cool about Python, these people who design Python are really smart, is that you can index backwards. Sometimes I just want to access the last 2 entries in the array. And if I can only access the array using forward indexing, to know the last index, I need to know the size of the array, which makes me want to write 1 more line of code to know what is the size of the array, and then call the array to access the last number. But what if we can index backwards? Well, turns out you can do. And the indexing becomes negative when you index backwards. Okay? Now, because we use 0 for forward indexing, we're going to start at -1 with reverse indexing. So now, A at -1, believe it or not, you put A, open bracket, -1, is going to give you 0.3. Because that's the last, always the last entry in any array is at -1. -2 is the second from last. -3 is the third from last, and so on. Okay? So A -1 is 0.3. A minus 5 is 33, right? It's this guy here. You don't believe me? Try it. Open your notebook. Okay? Please work, please work. All right, so let's say A is equal to np.array. It has to be a numpy array. Okay, and well, it doesn't have to be a numpy array, but we're working with numpy arrays here. Okay, so A is numpy array, and let's say, what was it, 5.4 and 7.2 I had, 7.2, 33.0, 21.2, 7.8, 10.1, 0.3. Okay, close the parentheses. Okay, so A0, you know, you can practice this. A0 is 5.4, A1 is 7.2. Now A minus 1 is 0.3, A minus 2 is 10.1, A minus 3 is 7.8, and so on. Very simple. Okay? Again, so remember, why am I doing this? Why am I introducing array slicing? Because I have an array now that contains the derivatives. I claimed that there's a really clean way to compute the errors without even writing a single for loop. But we have to use array slicing. The first step in learning array slicing is to learn indexing. So now you have forward indexing and backward indexing. You can index the array backwards or forward, however you like. And trust me, there will be times where like, oh crap, I need to access the last from second entry in the array. A minus 2. That's it, you got it. Or the last entry, A minus 1. It will show up. It will come when we are dealing with boundary conditions, and especially when we go in 2 dimensions, like heat transfer in a block or mass transfer, you know, in a cylinder. You're going to need to find the boundary, the edges of the array. And you can index them backward from the other side or from the beginning. Okay. Now, great, good. Thank you, Python gods. Okay, now, what we can also do, and this is where the power of Python comes in, is that we can also grab subsets of any array in Python. We can work with subsets. Say you have a lot of data, and you're like, okay, I only want the data from October to November. Oh, grab the subset. What are the indices? Just grab a subset of those. We call those views, and we access those views of the array. It's like you're opening a window to the big array. You're opening only this window, and you're looking into a small piece of that array, and we access it with slicing, the approach of slicing. Now, slicing takes indexing to a whole new level. Instead of a single index to access a value in an array, now you put 2 indices. What do these indices correspond to? To where you want to start your view, to where you want to end it. Okay? So this returns a view of the array that contains the element A at start plus 1, all the way to A stop minus 1. So remember that. It's like an open interval. Okay? So note that the element at the second index is not included in the view that you return. So it's like an open interval. This becomes clearer with an example. So for instance, A02 is going to return A0 and A1. A0 and A1, right? It's going to return this. Let's try it on your notebook. I told you I will not teach you Python, but in a way, this is like half of what you need in Python. Okay, so this is my array, A0 and then semicolon 2. It gives me what? An array that contains only 2 entries, which are A0 and A1. I can do A03. It will give me the array entries that contain A0, A1, and A2. Remember, we stop at the last index minus 1. So the last entry here is going to be A2, which is this guy. Okay? All right, so let's go back to the slides. Pop. Okay. Great. One more note to keep in mind. You're not going to really worry about this, but be careful that when you do this, even if you store it in a variable, which you should, store it in a variable, that's not a copy, a new copy, or a new array in memory. That new variable is still pointing to the original array. So if you take this and store it in a variable and then modify the values in that variable, it will also modify them in the master array, in the parent array. Okay? Just be careful of that. Okay? It's not a copy, it's a reference. It's a view that's still pointing to the parent array. If you change anything in the view, you're really changing in the master array as well. But the view allows you to do simpler operations on a subset of the array. Okay. Now you can also slice your way all the way to the end. So what if I want A3 and all the way to the end? Okay, I can just drop the last index here. If I drop the last index, it gives me everything from 3 all the way to the end. No questions asked. Okay? No questions asked. You can also index backwards. So I can go A3 to -1. Now remember, this is going to stop at A -2, right? Because it stops at the stop number -1, so it will be -2. So this will be from 3 to -2. You know what? If you're confused about it, and you forget how this slicing works, just create a new cell, create an array, put random numbers in it, and play around with it. So you remember where to start and where to stop. It's not rocket science. Okay, just try it out. If it works, okay, now you remember how to do it. Okay, I forgot, is it indexing from 0? And just write an array and try A0 and A1. Oh, okay, it's 0 indexing. Now I remember Python does that, and keep going, okay? So here I have a summary for you of how we can use this. So A start stop, it's the simplest, cleanest way of doing it. Starts gives you a view starting at A start and ending at stop -1. A start and then semicolon gives you everything to the end. And now if you drop the first number, it's always going to give you the first entry, so A0. So you don't need 0 at the beginning. And then it will stop at stop -1. And A semicolon without anything, it gives you a copy of the entire array. Actually, it's a view of the whole array. Okay, so now let's go back to our solution plan. Remember, those were our H values. Okay, there's an extra one here that I didn't put in the code. Next, we computed the derivatives, and we did directly this vectorized. We did the function x plus h minus f of x over h. And the result was an array that contained these derivatives. Okay, so this is done for a different function. But anyway, so this is the derivatives array. It's of the same size as the array that contained the h values. Because for each h value, there's a approximation to the derivative. Okay? At h equal 8, there's a value, 60.05. So this is done for a different function, not the one we were working with in the code. Okay, but just to illustrate the idea for you. In the code, that's where we left off. Agreed? We did the h values. We computed the derivatives. This is what we have. Now, I want to use slicing to compute the error. Okay? So this is what I just mentioned. Okay. To compute the relative approximate error, we need to take the difference between consecutive entries in the derivatives array. So why am I doing this? I spend more time on understanding what I want to do in the code, because coding takes me probably 1 minute for something like this. But I spend half an hour planning my solution. My PhD students hate me because I tell them, if you come to me without the math or without the pseudocode of what you're doing, I'm going to send you back, because I'm not going to work with just work. I need to see what you're doing so that you also see what you're doing and have a clear solution plan. Okay? So that's what I'm doing here. I want to understand how I can compute these errors, just kind of looking at this, planning my solution visually. So when I think about the errors, this is what we're doing. And look, once you visualize it, you get this eureka, this aha moment. The first error is based on the difference between the two subsequent values, right? Or the difference between the red arrow and the green arrow, right? That's 14.32 minus 60.05 over 14.32. Agreed? Great. The next error is going to be this difference, and so on and so forth. Agreed? So the errors, just as a side note, if this array was what? Size 1, 2, 3, 4, 5, 6, 7, 8 values, the errors, we're going to have 7 errors. Right? Because we're dropping one value. We're using 2 values at a time. So 1, 2, 3, 4, 5, 6, 7 errors. Okay? Now, if only, so if you look at this, we have here the values, the arrows in red, minus the arrows in green over the arrows in red. Right? That's what we're doing. We're taking the difference between the arrows in red and the arrows in green. So if we put the values that correspond to the arrows in red in their own array, and the values in green in another array, we can take the difference and divide and do the error, right? And this is where slicing comes in. This is where the view comes in. Because for the red ones, I want a view that contains 14, 7, etc., all of these guys. For the green arrows, I need a view that contains from the beginning until here. So I'm taking the difference between 2 views and doing the whole thing in one shot. Okay? So if I create an array or a view that contains the red arrows minus a view that contains the green arrows, right, it's going to do them one at a time. So the first, if I take the difference between these 2 views, is going to be 14.32 minus 60, 14.32 minus 60, 7.7 minus 14, 7.7 minus 14, 5.8 minus 7, 5.8, right? It's going to do that for us. Okay, so let's do this. I know you will review this video at home. It's very important that you do that. Because once we hit linear systems, I'm not going to stop for this. So you need to know this by heart. You need to have practiced it at home 100 times. Okay? My undergrads do this in their second year. Okay? So there's no reason that you cannot do it. Okay? All right, so let's go back here. I had these h values. Agreed. I had these df values, all of these df values. So let's call them let's call them red and green array, just because we did that in the slides, right? Just because we did that in the slides. All right. So the red values are going to contain. Okay, so the red values are going to contain this, and this. So all the way from index 1 to the end. Agreed? It's going to contain the values on the starting from this point all the way to the end. Right? So if you go back to the slides, that's what we had. Let me show you the slides. Here. Okay. So the red arrows, if this is my derivatives array, the red arrows start from index 1 all the way to the end. The green arrows start from index 0 all the way to the second one from the end. Okay? To the one before last, in other words. Okay, so how do we do this? The derivatives, red arrows. Okay, so look back at the slides. It's going to contain the df values starting from 1 all the way to the end. And if you're in doubt, print it out. Thank you. Okay, so that's the thing we say in my numerical methods course. Okay, if you don't know what this contains, just print it. Just print it. Let's see what it contains. df red arrows. Okay. So I wanted for the red arrows, I wanted the first entry all the way to the end. Indeed, this view, df values 1 all the way to the end, gave me 3.7, 1.99, 1.5, 1.3, 1.23, and 1.19. Okay? Good. So that gave me all the values of the derivative that are corresponding to the red arrows. Okay. Next, I want to do the green arrows, df green arrows. And that's going to be the green arrows are going to start from the beginning all the way to this guy. Okay? Not the last entry. So I will do df values starting from the beginning, I could put 0 or no number at all. And I'm going to go to -1. Okay, and then let's print it, df green arrows. Okay, so green arrows contains 15.5, 3.7, 1.99, 1.5, 1.31, and 1.23. Now I can check that these are of the same size, so I can subtract them and divide. All right, and now finally I can compute my errors. Errors is equal to df red arrows minus df green arrows, okay, in parentheses, over df red arrows. So that's better approximation minus worse approximation over better approximation, whether it contains a single value or 5 million values. It's just going to do it for you. No for loops, no copy pasting, no nothing. So enter. Okay, so let's print it out. Print errors. Okay. df red arrows minus df green arrows over df red arrows. Yep, so yep, that's the df red arrows, high order minus low order. Okay. Now I can put this in absolute value as well. Okay, and it's just going to give me the absolute value. Now let's compare this, and we can multiply by 100 to make them a percentage. Okay, so now compare this to what we did previously. So here we have the errors. 319, 85%, 32%, 14. If you go all the way up, look at that, 319, 85, 32, right? It's the same answer. But if you clean up the print statements here and all the comments, this is like 5 lines of code to do this whole problem. And it could work for any size array of H. Okay? Who thought that this was cool? Like terrified of this? Well, we're gonna build on this. We will build on this. This is still basic, okay? So I'm not trying to scare you, but I'm giving you a reality check that if you want to be competitive and do real work, this is just barely scratching the surface, but it's super powerful. Believe it or not, you can do 80% of the stuff just knowing 20% of Python. Anyone know the Pareto distribution, the Pareto principle? Yeah, so so the Pareto principle says that typically you can get, you gain 80% of the value by putting 20% of the effort. The remaining effort to get that up to 100%, you need 80% additional effort. So that's the point of diminishing returns. But you will know that this course will probably give you 20% of the Python, but it will do 80% of the job. The rest is for you to figure out, because some of you might do machine learning, some of you might be doing experimental data analysis, statistical, right? So that's where you invest the remaining effort, optimization, etc. But I will give you that 20% that will get you started so you can do 80% of the job, but you have to work with me. So you go home and work through this. If you don't work through this, you're going to fall behind, and then you're going to come back to my office and say, hey, how do I do this? I'm going to tell you, you got to go work it out, because I can tell when you did not make an effort to fix it, okay? Okay, let's go back to our slides. Now, the next question was to put this in a subroutine. Okay, we're not going to do that. Maybe I'll make it a homework assignment for you. To put this in a subroutine so you can calculate the derivative for any function. I'm not worried about derivatives anymore. The point of the lesson here is get you to do slicing. Now, go back and see what where you started in this course and where you're at now. Hopefully you didn't lose any information. Hopefully you gained some info, okay, some knowledge. We're going to document all of these little Python tricks that you've learned, and they're a finite number. We can put all of the things we're going to learn with Python on a single letter-sized paper. Okay, all of these things, like you learned import math, import numpy as NP, you learned how to give it a nickname, you learned slicing, numpy arrays, multiplying, adding them. You know, if you haven't done coding, this is really good now. Okay, next we're going to get a little mathy, and I'll introduce the idea of norms. Now, in the in-tech survey, I asked you about norms. Okay, so these are not like cultural norms, these are mathematical norms. That's what I meant by that. So vector norms or array norms. And I want to talk about that a little bit. Again, this is going to come and hit us later on, but I wanted to introduce it also to give you a flavor, just mix it up a little bit between some math and some coding. All right. Now, here's my story. Suppose that you are lost in paradise, whatever paradise is. To me, it's like a beach and coconut trees and just, you know, sand and like a cool breeze. That's to me just paradise all year long. Okay, and you are looking for the closest coffee shop. So this is like there's nothing there, but somehow there you're looking for a coffee shop because you want your avocado macchiato ginger cinnamon latte with almond milk sourced from sustainable farms and Arabian coffee beans from trees watered with distilled water and honey milk infused with the essence of chamomile. Now the chamomile has to be also grown with distilled water from fresh rivers. So you know what I'm talking about. Like a very fancy. Like I don't want that guy to be in front. I order simple coffee. Hello, can I have just black coffee, nothing with it. You know, it's just simple. But like sometimes there's a guy in front of me like ordering a fancy order. And I don't know how these baristas keep track of all of that, so bless them. But anyway, so you want that very special coffee, and somehow your phone in the middle of nowhere has a GPS signal, and you put that in your Google Maps. You say, okay, find me the Paradise Coffee or whatever you want to call it. Okay. So then the GPS tells you, okay, you go follow this direction, and you keep following the map. And then the GPS gets you to the coffee shop. Well, close enough, but from a technical perspective, it doesn't really get you to the coffee shop. It gets you within the vicinity of the coffee shop. Now, if you're doing like a precision targeting, a 1 meter error is a big deal, right? So you want to hit the target 100% with minimal error, right? So suppose that the GPS gets you over here, and you're saying, okay, I get to the coffee shop if the GPS gets me right here at that door. But the GPS puts you here, okay? And you are, let's say, 2.3 meters north, error in the north direction from the coffee shop, and 1.2 meters. So you're 2.3 meters south and 1.2 meters east, okay, from the door. So now technically, you might say, okay, we got to the coffee shop. But again, think of this if you're shooting a laser to do a surgery, or you're doing something with incredible precision and accuracy. Okay? How do you measure the error here? What is the error committed by this GPS? So I know I'm off 2.3 meters in this direction and 1.2 meters in the east direction. But what is the error?
It depends on how precise you want it.
I want to be right at the red door. And I'm giving you, this is the error in the north-south direction, and this is the error in the east-west direction. I'm giving you the error. But there's two of them, right? So what is the error? The hypotenuse, so like the diagonal. You take the diagonal, okay? What is another error? What is that noise? Yeah, it's I think some of the steam as it gets trapped, and because I think we set it a little warm. So weather God, can you fix it? Thank you. So he controls the weather. That's very important for me. Okay, so what is the error here? So we got the hypotenuse, or in other words, the square root of each individual distance, correct? Okay, what is this the only error? Is that the error? Could we say that's the error? So I'm giving you the individual errors. I'm giving you the error in this direction and the error in that direction. You have any other ideas?
Well, there is not just the distance, it's the direction too.
Okay. But we're measuring that. So okay, even if you put it here, it's still an error, right? It's still a measurable error, right? So that could be quantified by saying, okay, it put us the wrong way towards the east, the south, or the southwest, etc. But in terms of number, what is the error in this GPS? So I agree, hypotenuse is one way to measure the error. Do you have any other ideas? Add them together. Sure. Yeah, you'd say.
I was going to say that.
Okay, add them together, just numerically. Okay. Or say, take the worst value, 2.3. The error is 2.3. Yeah, all of those are acceptable. All of those are acceptable ways to measure the error. When the point is, you don't always have a single value for the error. The point is that in practice, you might have 2 or more values of the error. And the question is, when I have 2 or more values, what is my error? The error is a singular word. You can't say, oh, I'm going to report my errors, and this is an error. Like, what is the error in your device? What is the error in this GPS? On average, statistically, whatever, one error. You can't report 50 or 1,000 errors. Oftentimes, you will deal with systems, like we will do when we're dealing with linear systems. We are going to have an error for each variable, for each unknown. You could have 1,000 unknowns. But how do you say what is the error of your entire system? So the point of this exercise is to make you think about how we can consolidate error more than two or more errors into a single number. Okay? So you could take the sum of all errors in all directions, or you can take the average. So you add 2.3 and 1.2 divided by 2. If you had 3 errors in 3D, for example, you just divide by 3, right? Or you can take the hypotenuse or the Pythagorean magnitude, right? Or you can take the worst case value, the 2.3, right? This is the worst case scenario, and that's my worst error. And all of these are valid. All of these are valid. And you will see in practice, they are consistent with each other as long as you are clear about what error you are reporting. All right, now, in general, these numbers are an example of what we call a vector or array norm. Okay, we just did it with 2 numbers, okay, but in general, we can do this for an arbitrary number of entries in an array. I want to call it vector, but it's not a vector in the true sense, because vectors have certain transformation properties. So let's just call it array, which is a list of numbers. So when you have a list of numbers, you can combine those numbers together if they correspond to an error, or if they correspond to something that you want to report a single value on, just like you compute an average. If I give you, let's say you go to lunch every week and you want at the end of the semester, you want to figure out on average what your weekly budget should be. What do? You sum up all your spending for the semester every week and divide it by the number of weeks. So you took an array of spending, you added them all together and divided them by the number of entries, and it gave you an average number. So that's like your average spending. That's actually called a norm. Okay? That's actually called a norm. So we can define different kinds of norms. It's a mathematical operation that works on a list of numbers, on an array of numbers. The one norm, or what's called the L1 norm, simply takes the sum of the absolute values of all of the entries in the list, okay? And it's designated, all norms are designated by these 2 vertical bars. Instead of absolute value, you put 2 vertical bars. When I see 2 vertical bars, I know that someone is computing a norm, an average or some representative single number of a list of numbers. The under the subscript 1 here corresponds to the L1 norm, which is simply the sum of the absolute values of these guys, of the entries. Okay, so summation of ui is the summation goes over all the entries. I is simply an index. So u1 plus u2 plus u3 all the way to the last one. When I don't put the index here, it means I'm summing up over all the values. Okay, it's just simply the sum of all the values. It's called the L1 norm. The Pythagorean norm is called the L2 norm. Okay, it's designated by these two vertical bars with a subscript, and it's the square root of the sum of the squares of the entries. Okay, so square root of sum of the squares. Now, the worst case value, like in the previous example, 2.3, is called what? The infinity norm. Okay, it simply takes the maximum value in your list of entries in absolute. Okay, take the absolute value. The maximum entry, that's the worst case scenario, or the largest value in absolute values, that's your L infinity norm. Okay, that's the infinity norm. So your maximum spending throughout the semester is the L infinity norm of your spending array. Okay? The L infinity norm of the error in the GPS is the maximum distance that that GPS error has committed across all distances. Okay? So same thing, you know, for any array, whether be it an array of errors or an array of numbers, you can define these norms. Now, this will become more relevant when we are doing linear systems or nonlinear systems, where you have more than one variable. And as you are trying to solve the system, every step in the solution, you are committing an error. You can measure that error approximately. But then you have a list of errors because you have many variables. How do you say your system is done? What is the worst error? What is the average error? You got to compute a norm for that. Okay? Now, in general, so this is these. Okay. Let me rewrite this now to generalize the idea of the norm. Is that concept I promised to teach you in the syllabus. I will teach you about norms. Because in mass transfer, you will need it as well. Okay, so if this is the L1 norm, now observe the math a little bit. And this is the L2 norm. It's E2 and square root of summation of E squared. I want to rewrite this for a second. Okay, that's called the L2 norm. I want to put this, take the square root and put it as a power 1 over 2. Okay? So L1 is the summation of the individual values. L2 is the summation of the individual values squared. Connect the 2 with this 2. To the power 1 over 2. Connect this 2 with this 2. Okay? So now in general, now let's see, what do you think is the L3 norm? Okay. To the power 1/3, but what's under the summation? E cubed. Thank you. Turns out you can define other L norms. Okay, this should be in absolute value as well. Actually, so I'll fix it before I upload the slides. But you can define any kind of norm. L3 norm is the summation of the entries cubed to the power 1 over 3. Okay, and in general, you'll define the LP norm, which is the summation of all entries to the power p, all to the power 1 over p. We just use the L1, L2, and L infinity because they are the most common. Rarely anyone computes the L3 or L4 norms. I've never seen it. We typically work with the L1, L2, or L infinity norm. But some theorems in math, they require some p norms. But you should know it. You should know what this norm is. Okay? Now, in Python, thankfully, there is, so you can do this with NumPy arrays, or you can use a built-in routine in Python that comes from NumPy. So numpy.linalgebra, we will be using this other library next, but this is just a new library I'm introducing today, linear algebra library, .norm, and you give it an array, and you give it the order, and it computes the norm for you. It computes the norm. So let's try it out. So we go back to our Python. So let's say I have this list of errors here, these errors, and I want to take out the percentage. Okay, I want to deal with percentages. If I go and say np.linalgebra.norm and put errors here, and then comma, that's the order of the norm that I want, ORD. If I do the one norm, that sums all of them up. Okay, it's going to give me 4.6 61. If I do the L2 norm, it's going to take the square root of all of these squared, sum of them squared. And if I want to do the infinity norm, I do mp.inf. So that should give me the maximum value, which is 3.19. Indeed, it gave me the maximum value of 3.19. Okay, that's how you compute norms. Now, you can document this. We will be using it later. I have, 10 minutes left. I'll introduce this movie and just let you go instead of giving you a break and then doing the movie. So I'll just play this short clip and then let you go, okay? Because we're done with this first exercise on coding. What you need to do, you need to go and redo this. As soon as I upload the lecture or whatever notes you've taken, you need to go and study this and push yourself to the limit with it. Play around with the arrays, play around with slicing. I don't have to tell you what to do with slicing. You're a grown up, you can take that slicing and ask a question. What if I do 0 to -5 slicing? Let it crash, let it give you an error. Okay, and then come and ask about the error. I'm happy to help with that because then I know you're making an effort, you want to learn, okay? But you should go and do this. I'll upload the lecture as soon as I get back to the office. We're done with this preliminaries. We are gonna get into actual practical stuff. And the first unit is going to be on solving algebraic equations. We will be solving systems of linear equations and single and systems of nonlinear equations in the next unit. First is going to be on linear solvers, and I will start with a little movie to kind of set the stage. Let's see. I might need to fix the audio again, like last time. MacBook Pro speakers. Okay.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in the injury of 7 Prince George's County firefighters. On February 24, 2012, a wind-driven fire in a condemned single-family residential structure resulted in the serious injury of an officer and forcible entry firefighter from Truck 809 of the Prince George's County Fire Emergency Medical Services Department. NIST examined the fire dynamics of this incident at the request of the department. At 9:11 in the evening, a call was dispatched for a residential structure fire in Riverdale Heights, Maryland. Truck 809 was the first due truck and arrived on scene within 3 minutes of the dispatch. The 809 officer observed smoke moving extremely fast through the front yard and across the street. The Truck 809 officer and forcible entry firefighter proceeded directly from the truck to the front door of the structure. Less than 1 minute after the arrival of Truck 809, officer and forcible entry firefighter, both in full PPE and SCBA, have entered the structure and began their primary search of the first floor. Smoke and heat conditions on the first floor worsened, and the front door slammed shut, trapping the 2 members of Truck 809. Within 30 seconds of the door closing, the Truck 809 officer cleared a portion of the living room window on the front of the structure and exited to the outside. Truck 809 forcible entry was unable to self-evacuate and continued to endure the elevated thermal conditions in the living room. Although Truck 809 officer had sustained injuries and damage to his SCBA, he alerted other firefighters that his crew member was still inside. Fire attack had started from the basement door on the rear of the structure. The front door was reopened, and a group of firefighters, including the Truck 809 officer, entered the living room, found the downed firefighter, and pulled him outside through the front door.
In February of 2012, had a fire on 57th Avenue in the Riverdale Heights community. It's a single-family house, just like any other small single-family home in the county. First arriving units reported smoke and fire showing from a basement level. It's about 9 p.m. It was a red flag day, meaning the Weather Service had instituted a red flag warning for high winds and dry conditions. The truck and the engine arrived together. Truck crew of 2 for the inside crew went ahead of the engine line. They were going to initiate a search, what appeared to be an occupied home. They made it in a front door that had a swing opposite what you would consider. So instead of swinging to a wall, the swing was into the middle of a room. Fire was in a basement below them. When they entered, the hose line had not made it in the door, and the energy from the flow path that was now created coming up from the basement steps and now out the front door that they had just opened, that energy slammed that front door shut behind them. Within a matter of 2 minutes, those first two firefighters became trapped, and one of them incapacitated. The one smaller of the two was able to bust out one window, which was not big enough for him. Of course, that created another flow path. He got to a bigger window, bust that out, created a bigger flow path, but he was able to get out. He was then able to get the engine crew, who was still on the front porch, had not made entry yet. He was able to get them to help him force open the front door and pull the other young man out. That young man was in the burn center for 45 days, nearly lost his life.
NIST's Fire Dynamics Simulator, or FDS, was used to provide insight into the dynamics
A couple
of
more
destructive
minutes,
fire.
okay, but I want to
The
make this
results
point
of
here.
an FDS simulation are visualized with another NIST program called SmokeView. The inputs and details for the FDS simulations are documented in NIST Technical Note 1870. The fire started in the basement near the windows on the rear of the structure. Based on an assessment of the fuel load in the burned area of the basement, the estimated peak heat release rate of the furnishings and interior finish was approximately 9 megawatts. However, the lack of oxygen limited the fire growth until the front door was opened. As seen in the heat release rate graph, after the door was opened and allowed additional oxygen to enter and mix with hot fuel gases in the basement, the fire heat release rate increased, with some of the burning occurring on the first floor. Comparison of the simulated initial fire conditions in FDS versus the post-fire damage of the exterior of the basement corner, where the fire started. The wind was blowing from the rear of the house to the front. In the model, a steady wind speed of 20 miles per hour was used. The output from the FDS simulation can be used to provide insight to the flow path within the two-level structure. Fire gases move from regions of higher pressure to regions of lower pressure. Notice on the outside of the structure that the upwind side of the house, or the rear of the house, is under a higher pressure than the downwind side, or the front of the house.
So green,
The
blue,
inside
blue
of
is
the
low,
house
red
being
is
pressurized
high,
by
green
the
in the
wind
middle.
From the openings on the rear side and the pressure from the fire gases. Once the front door is open, the high pressure on the rear of the outside of the house and the inside of the house equalize. One of the hazards to firefighters located in the exhaust portion of the flow path is convective heat transfer from the fire gases. Convective heat transfer depends on the velocity, the amount of turbulence, and the temperature of the fire gases. This video shows the change in gas velocity on the first floor after the front door was opened. Notice the distinct flow of hot gases from the doorway at the top of the basement stairs to the front door.
So they open the front door, the air comes out from the
10
basement.
to 20 miles per hour would have impacted the front door and forced it closed behind the Truck 809 crew. This video shows the calculated change in gas temperatures as a result of opening the front door.
So red is
which increased the
800
flow and
Fahrenheit.
mixing of the fire gases
Green is about
within the
600.
house.
It's a very hot environment. Okay.
Wind can generate hazardous
Okay,
thermal
so I'll
conditions
stop
within a
here.
flow path.
You can watch the video. It's a long video, but the point I want to make is that, so this is actually my research area in computational fluid dynamics. So this technique where to calculate the temperature and the wind condition and the airflow and all of those things requires you that you calculate temperatures and velocities at many small points in the entire house or the entire system that you're working with. And oftentimes you end up with systems of equations for each variable at every point. Those equations can be linear or nonlinear. And this is the motivation to study systems of linear and nonlinear equations. Just this whole video just to get to this point. So we will do this in a one-dimensional problem, and then later when we get to partial differential equations, we're going to try to do something in either with time or in 2 dimensions in space. Okay, but that's kind of the motivation. I'll remind you of this on Thursday, but yeah, you're good to go. Thank you for today, and Godspeed.